Good evening, everyone. Welcome to today's discussion. Today we will be going through the topics taught in the week 4 lecture, and we will be revising all the topics that were taught in the week 4, and then we will be actually solving some of the problems based on those topics. So I hope that it will be beneficial to everyone watching this video. And if anyone has any doubts regarding any problem, has any question regarding any concept, then they may contact me anytime. I had my you can write in a discussion in your um, discussion portal, or you can even write in the comments of the YouTube channel where I will be uploading this video, and you may also contact me over email. Okay, so today's topic will be mostly based on some concepts of permeability. Permeability was already started the previous week, so we will be dealing with some concepts of permeability, and then we will be also looking into seepage. So we will be seeing what is seepage, and uh, how to how to calculate seepage forces and all everything. So we will be seeing all those things. So let us start one by one. So we will be starting with permeability, then we will be heading towards the in situ stress, the seepage along with the in situ stresses. Okay. Okay, so let us start. So our first topic is laboratory determination of hydraulic conductivity. That means laboratory determination of the permeability value, means K value. Okay, hydraulic conductivity means coefficient of permeability. So how to determine the coefficient of permeability or hydraulic conductivity of any soil? Okay, how can we determine this in the lab? So we will be looking into this in the beginning. So generally, say we have a soil sample. So generally, there are two main types of tests. Okay, two main types of tests uh, using which we can determine the hydraulic conductivity. Okay, so the first test is our constant head test, and second test is the flowing head test. Okay, so the constant head test is actually used for granular soil, so and the flowing head test is actually used for the fine grained soil. So why constant head test is actually used for granular soil, we will be discussing on it, and why flowing head test is used for fine grained soil, we will be discussing in this topic towards the end of this section, after we discuss the details about this test. Okay, so first of all, let's see what is our constant head test. So in constant head test, we have, so the main concept here is that the in constant head test, head the head of the water is actually maintained. Okay, so here you can see that, so soil is actually placed in this region. Okay, so here we have porous stones, and between the porous stones our soil is placed, right? So our soil is placed between the porous stone, and the head is maintained at h. Okay, so there is a head difference of h between the inlet here and the outlet here, but the head difference is maintained as h, small h, throughout the test. Okay, this head difference is not changing as the test progresses. This head is always same throughout the test. Okay, so small h is our head which remains constant throughout the test. Fine. So soil is there, and what happens is here there is constant water supply, so that the head is maintained at small h. The head does not reduce. So water will enter through the soil and will come out through here. Okay, so the extra amount of water is collected here. Okay, so what we will be doing is that we will be calculating the time t. Okay, we will be calculating the time t and the volume of water collected here. So in time t we will be collecting q volume of water in this graduated flux. Okay, so in time t q amount of water will be collected in the graduated flux. So what can we write? This q volume, it's actually nothing but area into the velocity of flow into time. Okay, so area into velocity small q is nothing but the flow, and t is the time. So we can write area into k into I into time. Okay, so my k is my hydraulic conductivity or the coefficient of permeability, and I is my hydraulic gradient. So what is my hydraulic gradient? So I know my hydraulic gradient, right? So my hydraulic gradient is nothing but the head loss divided by length of flow. So my head loss, which is small h, divided by this length, which is my length of flow L. This is my hydraulic gradient, right? So A into K multiplied by H by L into T. So if we rearrange, we can find out Q easily, isn't it? If we just rearrange the terms, we'll get K is equal to QL AHT. So using this expression, we can find out the hydraulic conductivity of the soil. So we know this volume, we know this length of flow, we know the area of cross section of the soil sample. Okay, we know the head loss, we know the time, we can calculate. Okay, so the next test is the falling head test. So in the constant head test, actually there you saw that there is a constant supply of water, uh, due to this constant supply the head is maintained, right? The head is always h, small h, it's maintained at small h, isn't it? So the head is always maintained. But in falling head test, what happens is that the head is allowed to reduce. There is no external constant supply of water, due to which the head reduces. So here same, see, this is my soil kept between two porous stones. Okay, water is entering through the here and exiting through here. So my head will be reducing because there is no constant flow, so my head will be reducing continuously. So what we need to measure is the time t1 at which my head was initially h1, and then at time t2 my head is actually what, h2, right? My head reduces, head is h2. So in time t2 minus t1 my head falls from h2 to h1 to h2, right? Now see, now I will just derive it very fast because this has already been taught in the class. So what happens, so the rate of flow at any time is nothing but q is equal to kia, where I is the hydraulic gradient, so k into h by l into a, right? H is the head at any point of time, right? Head here, h is a variable, which is a variable, and h is a head at any point of time. And also you can equate it to small area means area of this tube, okay, small area into dH by dt means the rate of change of head into this area of this pipe. Okay, negative because with increase in time my head is reducing, that's why we are giving a negative sign, right? So we can just rearrange it, AL by AK into minus dH by h. Okay, now you just integrate this from 0 to 2t or t1 to means 0 to t or t1 to t2. Okay, all the same, 0 to t or t1 to t2. T is actually t2 minus t1 is my t. So here I am just setting it 0 to t, right? And this we can integrate from h1 to h2. So if you do this and rearrange, you will get your expression as t ln h1 by h2. So in time t, my head reduces from h1 to h2. Okay, here A is the area of cross section of this pipe. A is the area of cross section of the soil. T is my time in which my head reduces from h1 to h2. You know h1, you know h2. From here you can measure h1 and h2. So you can find out the k. Now the question comes, why is falling head test used for fine grained soil and why is constant head test used for granular soil? Okay, the answer to this is very simple and very intuitive. See, our intuition says that if the soil is granular like sand or gravel, what will happen? Those are more porous, permeability is very high. What happens if you put if you means put pour water will instantly pass through it, right? So the flow water will be very fast through it, isn't it? So it is very difficult to measure the time, the head reduction time, because h1 to h2 head will reduce very fast. Okay, very fast the soil will go. That's why constant head test is used. Okay, and in falling head test, what happens? The fine grained soil, the pores are very small, so the water takes more time to pass through the soil. So it's easier to measure the time, the fall of head from h1 to h2. It's easier. It's easier to note the values, right? So that's why you use falling head test for our fine grained soil. Okay, so for falling head test is for fine grained, and my this is used for granular or coarse, that is coarse soil. Now let us see some of the empirical relations for hydraulic conductivity. Okay, so what is the detent size? If I ask you, if you remember, detent size is nothing but my what size? There is a name for detent size, right? Right. So detent size, there is a relation between our detent size and the hydraulic conductivity K value, right? So this relation is simple. It's nothing but K in cm per second is equal to C into d10 square. Or C is a constant. The value is between 1 to 1.5. Okay. And what is d10? The d10 is my effective size, right? D10 is my effective size. Okay. So effective size in millimeters. Correct. So if you know the effective size, okay, you can determine the K value. Next, Casagrande also proposed a relation. Okay, so you have K is equal to 1.4 e to the power K 0.85. So if we know the hydraulic conductivity at a void ratio of 0.85, using this relation we can find out the hydraulic conductivity at any void ratio E. None. Then we have the Cosen Bosonic-Harman relation. So Bosonic-Harman relation is that my K hydraulic conductivity is proportional to E cube by 1 plus E. Okay, so we can write it as E K is equal to C1 E cube by 1 plus E. Okay, so this C1 is a constant which we can obtain by getting K at two E values. Okay, two different E values, and then we can solve the equation and get the C1. Now comes equivalent hydraulic conductivity in vertical and horizontal and vertical flow. Okay, it's equivalent hydraulic conductivity. So what is equivalent hydraulic conductivity? Equivalent hydraulic conductivity is nothing but when my flow is in stratified soil. Say you have a soil like, okay, I will just draw it bigger. Okay, so you have a soil like this. Okay, this is a stratified soil. Okay, so this is H1, H2, H3 and Hn. Okay, so depths are different, right? And each of these layers, say they have different k values in two directions. In horizontal they have one value of hydraulic conductivity, in vertical they have one value of hydraulic conductivity. This is kh1 kp1. Similarly for all this also we have different in both directions. Now say my direction of flow is this horizontal flow, my water is flowing through this direction. So first we will be seeing for horizontal flow. Okay, so say our flow is horizontal, right? So if our flow is horizontal, so what can we say? Say we can say that the total, see the flow in each of this will be equal. Okay, so my total flow, some input is there from this side. Okay, some output will be getting from this side. Okay, think in this way. So we'll be giving some input, water is flowing into the soils and then getting divided into all these parts, and then we are getting an output. Okay, equivalent output we are getting. Think it that way in terms of say electricity. Okay, electricity, it is easier to visualize that way, right? Electricity gets divided like this, like flow of current get divided. So then we are getting an equivalent output, that's it. Okay, now we want to determine the equivalent hydraulic conductivity of these layers when the flow is horizontal. So when the flow is horizontal, my total flow q is equal to v into 1 into h. Capital H is the sum of, when h is the sum of h1 h2 dot 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 up to hn, means this height, total height of the stratified. Okay, and v is the velocity of flow. Which what velocity of flow? Average discharge velocity. Okay, and 1 is actually the cross section unit we are considering, that is, say there is unit cross sectional area out of plane, is out of plane, there is unit cross section area out of the screen, right, perpendicular to the plane of the screen, out of plane, it is unit cross sectional area is there, correct? So this can be written q is equal to VIH. Okay, total flow, we can write this v into 1 into h. Okay, now this q you can also write is equal to v1 into h1 plus v2 into h2 plus dot 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 plus vn into hn. That is the sum of the flows in all these, sum of the flows in all these channels all these soil layers is equal by this, right? These V's are the discharge velocity in each of these layers, right? In each of these layers, this is my discharge velocity, correct? Now we can write V as V is equal to K horizontal equivalent into I equivalent, right? V1 is equal, we can write as KH1, this KH1 into I1. Like this we can write for Vn also, this is KHN into In, right? Now if we look into this, our head loss is always same. From this side to this side, from this side to this side, my head loss is same, right? Head loss is going to be same for all the layers. My head loss is going to be the same. Okay, my head loss is same. That means what? My hydraulic conductivity is same because the flow is also occurring through same length. So my all the hydraulic conductivity I1, I2, all these things are equal to, all the hydraulic conductivities are equal. So what we can write is finally KH equivalent is nothing but KH1 H1 plus KH2 H2 plus dot 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 plus KHN HN divided by H. So this is my final expression for the equivalent hydraulic conductivity, right? So we got the, this is the expression for the equivalent hydraulic conductivity for flow in horizontal direction. Next we will be looking into vertical flow. So before in the previous case we saw that our heads are same, but what will happen when the flow is like this? My input is this side, my output is this side. In that case there will be separate, means the head losses will be different. The total head loss will be the sum of the head loss in this layer plus this layer plus this layer plus this layer, isn't it? Flow is occurring vertically, so my head loss, there will be the total head loss will be the sum of head losses in all those layers. Okay, but what will be same? The flow will be same. So by continuity principle the flow should be same in each of these layers. That means the velocity of flow means v1 v2 v3 vn will be same along all these layers from the equation of continuity, isn't it? So we can write vertical flow, my v is equal to v1 is equal to v2 equal to v3 equal to dot, 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 equal to vn. Okay, and my total head loss is equal to head loss in layer 1 plus layer 2 plus layer 3 plus head loss in layer n, right? So now my k vertical equivalent into ki means h by h. My total head loss is h, head loss occurring along length capital H is equal to, I am just writing this expression. Okay, h is equal to v1, so kv1 into h1 by h1. Okay, this is nothing but I1. Similarly, kv2 into I2 dot dot kv3 into IN, right? You can write like this. Now my H is nothing but equal to H1 into I1 plus H2 into I2 plus dot dot plus Hn into In, right? This is the height, depth of each layer, and this is my what? Hydraulic gradient. So if we solve this equation and my this equation, okay, you will get my equivalent vertical hydraulic conductivity as Hy H1 by Kv1 Kv2 plus dot 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 Hn by done. So this is my final expression, right? So in horizontal flow, my head loss is same across all the layers, and my flow is the sum of flow, or the velocity is the sum of velocities in all the layers. In vertical flow, my head loss is not same. Head loss is the sum of head loss in all layers, and but my velocity in all layers are same opposite. Now the next topic is how to determine in situ, means how to determine the hydraulic conductivity of in situ. Hydraulic conductivity means uh, in the field. How can we determine, means without taking the soil from the field, without disturbing the in situ condition of the field, how can we determine the hydraulic conductivity? Okay, so this is the next topic. So in the field, how can we determine the hydraulic conductivity? Okay, one is a lab test, another is a in situ test, right? So how can we determine the hydraulic conductivity in situ without taking out the soil sample, without disturbing the natural state of the soil? How can we determine the hydraulic conductivity? So the first my first topic is using porous probes. Okay, so the porous probes are nothing but there are some probes which are pushed into the soil. Okay, pushed into the soil, and then water is allowed to come out of those probes. Okay, so there are different types of probes, such as the constant hydraulic this one constant head hydraulic conductivity test, which can be done using the porous probes. Then nothing or K is given by Q by F into H. Okay, so F is one of the parameters of that relating to this my instrument. It's this porous probe. So what is done is that these porous probes are actually pushed into the soil, and the constant head or falling head tested then. Okay, so for constant head, this is my relation. Okay, and falling head test also can be done. So in falling head test, there is, just write it down. So this is same as the whatever we learned for the falling head test before in lab test. So here we have the area of the tube. Then we have a constant F. Then from T2 to T1 we are observing head drop from H1 to H2. In this time we are observing head drop in H1 to H2. So using this relation we can find out the hydraulic conductivity. So there are many types of porous probes. There is a permeable base. It has permeable base, some have without impermeable. So those relations were already discussed in the class, so I won't go through that again. Okay, so now this is very important test. This is the pumping out test. This is known as the pumping out test. Okay, so in pumping out test, what is done is, so this is my soil, right? So this is my ground level. So a main well is dug into the soil. Okay, and this is the impermeable strata. Say it can be like hard rock base or something. It's impermeable, right? So this is my impermeable stratum, and a well is actually drawn. Actually, well is actually constructed, dug out in the soil. Now what is done is that one is the main well, right? Test well, this is known as the test well, and there are also two other wells dug. Those are known as the observation wells. Okay, so total three number of wells are dug. So one is my main test well, another is my two other are my two observation wells. Now what is done is, using a pump. So this is my water table, right? So this level is my water table well. Okay, and it is done. So what happened, as the water table is here, so there will be water up to this level, right? If we dug a well, as the water table is in this level, so my water will also remain up to this level. What is done is, A pump is used to actually constantly pump out water from the test well. Okay, so constantly it is used, pump is switched on and the water is actually pumped out of the well. Okay, so after some time it is seen that this attains a like certain like a fixed volume of flow is coming out. Initially it will be high, so this is done actually up to which that like say we will be pumping out the water. Okay, so after some time a steady state will be achieved. State will be achieved means this height will be steady. Okay, a constant flow of water, outflow of water will be achieved. Okay, so what happens, so actually what is happening inside is that this is, so we are pumping out water from the main well. So what happens, this the water actually forms a curve like this, is known as the drawdown curve. So when there is pumping the water, so see at L, as we go further away from this main test well, a water level is actually reaching the main water table height, but as we come near to the test well my water is actually reducing. Okay, so this is known as the drawdown curve. So obviously the test observation well which is nearer to my test well will have a water depth which is more. Okay, and this will have water depth which is less, obviously, because this will follow, water is following my drawdown curve, right? So what we can write is that, yeah, so we can write, so water is being constantly pumped out. Okay, pumped out from this test well, and after a certain time it is seen that this height has become fixed. Okay, so this height and this height is say, or you can say h2 and h1, this has become almost fixed, these are not changing, means steady state has been achieved after for the drawdown, right? So we are pumping out and that steady state has been achieved, these h2 and h1 are not changing anymore. So what we can write is that my small q is nothing but a flow means the flow at which water is being pumped out of the well, right? Which is equal to k is the hydraulic conductivity into dh by dr by twice pi r h. So k is my hydraulic conductivity, dh by dr is my hydraulic gradient, and twice pi r h is nothing but the area, means which area, this area, means any area, means this age, right? This variable height, so we are taking means actually age means the area through which water is actually entering into the well. Okay, so this is soil, right? This is soil region, so water is actually entering the well. So age is the twice far age is the area which is contributing to the refilling of this well, means water is flowing through those area into the well. Okay, so that is that area twice fire h. Now if we just rearrange, okay, r2 r1 dr by r equal to twice pi k by q h2 h1 h into dh. Okay, so now if we just integrate we can find the relation as q ln r1 by r2 by pi h1 square minus h2 square. Okay, so using this relation we can find out the hydraulic conductivity of the in situ soil. So this q you know, because you are pumping out the soil at a constant rate. Okay, that rate you know, at what rate water is being pumped out of the oil. Okay, so that rate is known, flow rate is known, which is nothing but small q. r1 and r2 are also known. r1 and r2 are nothing but the distance of the radial distances of the observation well from the test well. These are also known, and my h1 and h2 are also known. So we will be measuring this height, right, up to which the water is below in the observation well. So h1 and h2 also we can know, because total height we will be knowing. So this minus this h1 and h2 we can find out the height. Okay, draw down, you can find out the height. So H1 and H2 will be also be known. So using all this in this relation, we can find out the in situ hydraulic conductivity of the soil. Okay, so we will be solving problems towards the end. Together we will be solving after we go through this topic. Yeah. So the main permeability topic is over. So the next topic uh, which we will be dealing with is seepage. So seepage is nothing but the flow of water through a soil mass, right? Flow of water through a soil mass. So permeability, what is permeability? Permeability is a property of the soil through which it allows the flow of water or any fluid through it, right? And what is seepage? Seepage is how the water flows. We will be looking into the thing there, how water actually flows through the soil, and what is the actually how we can actually formulate, how we can mathematically represent that flow of water into the soil. Also, why seepage is the study of seepage is important. The study of seepage is very important because say we have some many offshore structures, offshore structures like say what the sheet pile walls and those things, right? So in the sheet pile walls, we need to determine the flow, okay, the flow of water which is crossing our barrier, sheet pile. And also say in the case of dams, earth dams. So in earth dams, we need to find out what is the water that is seeping through the earth dam, right? So we will be seeing how we can calculate all those things. So the main task in this chapter will be how to mathematically represent that flow of water through the soil so that we can calculate the flow of water uh, through a art dam or any other geotechnical structure. Okay, how we can mathematically, we'll see how we can mathematically calculate all those things, right? So so my flow of water in the soil is actually not in one direction, right? So it is not unidirectional. So flow of water occurs in soil in all directions, right? So flow will be occurring in all the directions. So actually we use the Laplace equation to define the flow of water in a soil. So how we can obtain the Laplace equation we will be seeing here. So see, so here we have considered a 3D soil block. So this is a soil block, right? It's an infinitesimal soil 3D soil block. So the length, you can see the length, width and height dx, dy and dz. It's very small. So it's d. We are writing dx, dy, dz means it is very small. So a small, very tiny section of soil we have taken 3D soil section. We have zoomed it and we are representing this one. So so this is my soil block. So vx is the flow of water along x direction, okay? And if we see dy dz into dy is nothing but this area of this face. So velocity into area is nothing but my flow. So this is my flow which is entering, okay? And what is the flow that is coming out? So it is traversing a dx path. So the flow which is coming out is vx plus dou vx by dou x dx dz dy. Similarly, in this direction also this is valid, in the other direction, this out of plane direction also this is valid. So all three directions we can write this. So yeah. So the rate of flow in inflow in horizontal direction, this is the rate of flow in horizontal direction, and the rate of this is the rate of outflow in horizontal direction. This is the rate of inflow in vertical direction. This is the rate of outflow in vertical direction, right? Now what we can write is that my rate of inflow is actually will be equal to my rate of outflow when my condition is that there is no volume change, means C. So here whatever we are studying is that this is not unsaturated soil, we are considering the soil is saturated. So there is another part of soil mechanics that is known as unsaturated soil mechanics, which is also a very vast topic. and actually it's very advanced topic. So in unsaturated soil mechanics, we do not consider the soil as completely saturated. If the soil is not completely saturated, there will be some volume change when the soil enters and soil exits. So there is some, we consider a certain volume change. But in this case, in seepage, the soil is considered as completely saturated. Okay, so if the soil is completely saturated, there is, and we are also considering that there is no volume change. Okay, whatever water enters, that same amount of water exits, and there is no volume change of the soil mass, right? So if we just equate the inflows and equate the inflows and outflows, you can easily write it as dou Vx by dou x plus dou Vz by dou z equal to 0. Okay, we will just equate the inflows and outflows of the soil. Now from Darcy's law, we can write as V is equal to K into I. Okay, Kx will be Kx, and what is my Ix? Ix is nothing but dou x by dou h by dou x. So dou h is the head loss along the path, this d dou x. Okay, so we can write this. Similarly, Vz also you can write in similar fashion. Vz also equal, you can write Vz equal to Kz into h by dou z. You can write. So now from if we substitute this into this, we will get kx into dou square x by dou x square plus dou square h by dou z square equal to 0, right? So this is my Laplace equation, right? So this is known as Laplace equation. So this is the Laplace equation when in my vertical and horizontal. So if we consider 2D soil mass, in my vertical and my horizontal direction, my hydraulic conductivities are different. So in the horizontal it is kx, and in my vertical direction it's kz. So the hydraulic conductivities are actually different. So the flow is actually non-isotropic, anisotropic. Now if my soil is isotropic, means the hydraulic conductivity is same along the horizontal direction as well as the vertical direction. It means my kx is actually equal to kz. Okay, that is the isotropic case, means in both the directions my hydraulic conductivity is same. So in that case we can simplify the equation as 0. So this is for isotropic case, my Laplace equation, right? So now let us look into the 1D so the 1D flow problem was like already discussed in very detail in the class. So I won't go into detail. I will just summarize it for you. So what we considered is that soil mass is there like this. So here we have one soil, and here we have second soil. So there is water supply. So water is entering this way, water is coming out the other way, right? So the head loss, everything is given to you, and this height is actually h1 and this is actually h2. All those things were given. So then what we did were first we wrote the hydraulic conductivity in 1D. So here we are considering that the flow is only in one direction, that is the vertical direction. So the Laplace equation will be changing into the 1D Laplace equation, this. Okay, so then we so then after integrating it, we can write this as a1z plus a2, where a1 and a2 are my constants, right? a1 and a2 are my constant. Then we can put the boundary condition, say at this side. Okay, at z equal to 0, my head, it was given as h1. When my z is equal to h1, my head was h2. These things were also given to you. The heads are known. So if we put this, we can get the values of a1 and a2. Similarly, we can again get the value of a1 and a2 for this region, this part. So first we obtain for this part, Then we obtained for this part by changing our boundary conditions. So we obtained two values of a1 and a2. Say a1 has two values, a2 has two values. So a1 and a2 is valued for upper region, a1 and a2 is valued for the lower region. Okay, so we determined this a1 and a2, and finally ultimately what we determined was that our head loss. Okay, so head loss means the head at any point, say here you want to find the head. How will you find out? So we solve the equations and we find out two equations which I am writing down here. So this is valid in this region and this is valid in this region. Okay, so at any point in this soil, if we want to find the head, we can use this relation, and at any point in this soil, this part, if you want to find the head, you can use this relation. So finally we determine this. So these actually don't need to remember something, no need to memorize these things. These things are actually conceptual. We don't need to, like, sometimes in exams what happens, these derivations are given for like checking the concepts of the students and nothing else. So these are very basic, okay, concepts. Next, now let us come to the main topic. The main topic of discussion is our flow net. Okay, so what are flow nets? So we saw our Laplace equation. Okay, dou square h by dou x square plus dou square h by dou z square equal to 0, right? So the solution of this surplus equations is actually given by a family of curves. So we know that, so in mathematics we have learned that the solution of second order partial differential equations can be represented using a family of curves. Okay, so flow nets are nothing but the solution of this Laplace equation. Okay, so we get two family of curves. Okay, so the one family of curves is known as the flow lines and the other are known as the equipotential lines. And these flow lines and equipotential lines actually form a net like structure which are known as the flow net, right? So my flow lines and equipotential lines are the solution of the Laplace equation, and both these flow lines and equipotential lines actually form a net-like structure which is known as the flow net. So using this flow net, we can actually determine the amount of flow across a hydraulic structure such as a dam or a sheet pile wall. We can find earth dam or a sheet pile wall or any other thing. So we can find this out, and also we can calculate the head at any point. We can calculate the seepage pressure, we can calculate the base pressure. So all those things we will be looking into one by one slowly. So these flow lines and equipotential lines, they have a very distinct property, that is they are orthogonal to each other. Okay, so orthogonal means they are perpendicular to each other. These flow lines and equipotential lines are always perpendicular to each other. Also in the flow net, say these are my flow lines and these are my equipotential lines. So this, at these points they are always perpendicular. Okay, so they are always perpendicular. Also always they almost form a square. Okay, so this region is always a square. Okay, the elements, flow elements, these are known as flow elements. So these flow elements are always square, right? Just a second. Yeah, so say we have a sheet pile wall. So this is my sheet pile, and here we have the upstream water, we have the downstream water, the head difference is h. Okay, so and here we have the impermeable base. Okay, so flow can only occur here in the above. There is no flow here because this is impermeable. Now, so we will be getting some flow lines like this, like this. There will be some flow lines. So I am just drawing it simply. So it will, okay, there will be some flow lines, and also there will be some equipotential line like this. Okay, so these flow lines and equipotential lines will always be perpendicular to each other, right? So they will always be perpendicular to each other. Now, this so what we do is that actually say we have, so this is the actual structure, right? So this is the actual structure which has been constructed. Now it has been asked to you, how can we calculate the seepage flow that is occurring across the sheet pipe, right? So how to calculate? So what we do is that we draw this sheet pile, everything in a particular scale. We scale it down, and using a particular scale we draw it in a piece of paper. After drawing our structure in a piece of paper, what we do is that we, by trial and error, we construct this flow line. So these flow lines actually need to be constructed, flow lines and equipotential lines both has to be constructed using trial and error, right? So flow lines which I will be drawing might not be same as which you will be drawing. The flow net which I will be drawing might not be exactly same as what you have drawn. So these are actually drawn based on trial and error. So the during while drawing, the two main criteria which I should satisfy is that the flow lines and my equipotential lines both should be perpendicular to each other. Okay, this is my first criteria. Okay, and the second criteria is that these flow elements which will be formed, they should be approximately square. So using these two criteria, you need to construct the flow net in trial and error. Okay, and there are some more properties. So this base line is also a flow line. Okay, so flow can also happen here, right? So this is also a flow line, and also flow can happen here, right? So this is also a flow line. These two are flow lines, correct? So now, using trial and error, we actually need to construct the flow net. So after we construct the flow net, we will be uh, having, we can calculate the total number of flow channels and total number of drops. Say here, these are the flow lines, right? And the space between these are actually known as the flow channels. So here we have 1, 2, 3, 4. 4 flow channels are there. Here number of flow channels are 4. And what are the this one? What are the number of equipotential drops? See, here to here there will be 1 drop, 2 drops. Okay, here from here 3, 4. Okay, total 4 number of drops will be there, right? So we have drawn the flow net. Then from there we can actually find out the total number of equipotential drops and total number of flow channels. So using those we can actually calculate the number of this one. This one will actually also be a flow, this one, my potential line. So using that we can actually calculate the total flow in, how much water will be actually flowing. We will be seeing how you can calculate. So here if we see again, so what are the number of flow channels? 1, 2, 3, 4 number of flow channels are there. Okay, and what are the number of equipotential drops? From here to here there is 1 drop, from here to here it is 1 drop, from here to here it is 1 drop. Total 3 drops this side, and total 3 drops that side. Total 6 number. So my number of flow channels are 4, and what are my total number of potential drops? Total number of potential drops are 6, right? And my here this is the case of isotropic case. It is my kx is equal to kz equal to k, means in both the direction, horizontal, vertical, my k is, that is the hydraulic conductivity value is the same, right? Just a second. Hmm. Okay, just a second. Yeah. So this is also a flow line, right? This is also a flow line. So these, so we should also take care that these are also always perpendicular. Okay, this is a flow line.
Markup is not coming.
Huh?
Your marking is not reflecting on board.
Now is it coming?
Yes.
Okay, 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 okay. I will just erase and do. I will just draw once again so that it's clear.
Sir, please.
Hello.
Hello,
Yeah,
sir.
yeah,
Please explain ND how 6 came.
yeah, yeah. I'm explaining. I will just draw it properly. Just draw it. Wait. Just draw it here. Okay, okay. So here is my sheet pile one, right here. Okay. So these are my flow lines and these are my equipotential lines. So always remember that these should always be perpendicular. Okay. As this is my flow line. This I am considering is it is a flow line. So this should always be perpendicular. Okay, and this one is also my equipotential line, so this also should be perpendicular. Okay, so by trial and error we need to construct. So now see number of flow channels, how see now, see I can draw one more. Yeah, so how I am saying nf is equal to 4 is that, see, here we have one, here we have two, another flow channel. I'll just change the ink color. Yeah, so here we have one flow channel, here we have second flow channel, here we have third flow channel, and here we have fourth flow channel. Okay, that's why we are saying the total number of flow channels are nf is equal to 4. And now the second thing is how number of drops are 6. So see, here to here one drop, here to here second drop, here to here third drop, here to here fourth drop, here to here fifth drop, and here to here again sixth drop. Okay, so that's how we are getting total number of drops as 6. Here to here is one drop, here to here is second drop, here to here is third drop, here to here is fourth drop, here to here is fifth drop, here to here is sixth drop. So you are getting number of flow channels as 4 and total number of drops as 8. Right, so this can actually change. Now if we draw more number of, see, if we draw smaller curves, then we can draw more. So it will, the flow net actually varies from person to person. It can won't be same, but always we need to make sure that my end conditions and my criteria are always satisfied. The conditions are that here it should always be perpendicular, because as we are considering these lines as a equipotential line and this is the flow line, so this should always be perpendicular. This line is my flow line, right? So this should always be perpendicular. Okay, we should always be taking care of this. Also these should always be perpendicular to each other. Also these should always be square. Okay, so these are the criteria we should follow, and keeping these criteria in our mind, we can, in the piece of paper, we can draw in trial and error. We can erase it and draw again and again. We can draw like this in trial and error. We can actually construct the flow net. So many softwares are also possible, like actually mm, uh, available, using which the flow net can be drawn. Now one thing actually can come to our mind is that, are these flow net actually imaginary? Means imaginary. So actually not imaginary. So if we actually observe these flow lines actually represent the path each water particle is going to follow while it flows. So these are not actually some arbitrary, these are actually the path follows. Actually physically my this Laplace equation actually in reality actually it represents the flow of water. So there are, see, you see there are some many software, say in abacus also, in abacus is a finite element software. In abacus also we can actually see that we want to simulate this, we can simulate the flow of water through a porous soil. So in that case also we will see that we are getting these flow lines. This flow lines means actually the water actually in reality the water actually traverses this path, these curves. So that's why mathematics is a very powerful tool, right? So using mathematics we are representing physical like how using mathematics we are actually representing how a physical system behaves in reality in terms of mathematics. It's helping actually a physics. So mathematics and physics are interrelated, right? So physical system is actually represented with the help of maths. So now the main one more topic is that this flow means how we can calculate the flow using this flow net. That was also, so I will just see, now there is no space here, so I will just make one. Yeah. Yeah, so we already saw that, if this one is my flow channel, so flow is occurring through here. So these are my equipotential drops. Okay, so these are always perpendicular. Okay, so my flow is actually occurring through these flow channels, right? So said this is a equipotential drop, means at all the points in that equipotential line my heads will be same. So here in all the points my head is h1, say, in all the points here my head is h2, say, and here at all the points say my head is h3. Okay, so in the equipotential line at all points my head is actually same. Okay, that's why we are calling it as equipotential line. Equipotential means same potential everywhere in that line, right? And say the length of this one is my L1, and say this one is P1, like that. Okay, so some flow is entering here and some same flow is exiting that part from our continuity equation, right? So the flow which enters is equal to the flow which exits. Now this q, this del q will be same everywhere. So del q is equal to del q1 is equal to my del q2 will be equal to del q3 everywhere. Okay, equal to del q1. So this q flow is actually same, right? From continuity equation my flow is same, my flow is not changing, and these are my heads. Okay, now we can write this del q as k into h1 minus h2 by l1 into b1. Okay, q is what? Q is kia. K is my hydraulic conductivity, I is the hydraulic gradient, and then A is the area. So we are considering the out of plane its unit length. So my area is nothing but this b1, b1, b1 into 1. Okay, so b1 into 1. So so while constructing our flow net, what we are always, I told you that we have to take care that always this should be a square. So if it is a square, my L1 is actually equal to B1. So we can write it as K H1 minus H2 by L1 into L1, right? Because this is a square. This is a square. Now this head drop. So H1 minus H2 is my head drop from here to here. Head drop and is occurring through L1. So this gives my hydraulic conductivity. Now these head drops, okay, so this head drops H1 minus H2, this H2 minus H3, all these head drops are actually equal, and this is actually equal to my total head divided by the number of drops. Okay, say, let us go to the previous. So say my total head here has capital H. Okay, from upstream to downstream, my total head was capital H, and the total number of drops were 6. So in each drop from here to here, the head loss will be capital H by 6. From here to here, my head loss will be capital H by 6. From here to here, my head loss will be capital H by 6. So in each drop, my head loss is actually same. It's equal to the total head loss divided by the total number of drops. Okay, so now we can write this as Q equal to K into H by ND, H by ND. So this is the flow actually occurring through one flow channel, right? So one flow channel, this is the flow that is occurring. This is a flow that is occurring through one flow channel. Now there are NF number of flow channels. Here there were four number of flow channels. Okay, NF number of flow channels. So what will be my total flow? This into NF. Okay, so this will give my total flow. So this is the flow for in one flow channel, and this is my total flow along NF number of flow channels. Okay, so if we draw the flow net, if we know the total in the upstream side, in the downstream side, if we know the head difference, and we can, if we also know the NF and ND, means it is the total number of flow channels and total number of drops, we can calculate the total amount of the total flow of water that will be happening. Okay, so the flow net actually is a very important tool which helps us to determine the flow. Okay, just using by drawing, simply by drawing on a piece of paper, we can calculate the flow of a structure, flow through a structure, hydraulic structure. Okay, now the next thing comes is there for anisotropic soil. Yes. Yeah, so for anisotropic soil, actually my kx is not equal to kz. So in this that case, our this uh, our formulation of the formulation, see, our Laplace equation was what? K is square h by z square h by rho x square. Okay, so this formulation is valid. So in this case, actually how our flow actually happens, how the flow actually differs, and how in this case we can draw a flow net. So this we will be actually looking in detail in the next class. Okay, so all these things in an isotropic flow, how our flow is there, and also in an isotropic soil, how my this how we can draw the flow net, and then we will be looking into how we can calculate the seepage pressure and all those stuffs we will be looking into next week. So now, and also regarding these things, how to calculate these flows, we will be doing solving some problems in the next week. So this was actually this NFND, this part was actually this derivation was actually taught in the 5th week, but still I just uh, decided to discuss a little bit here because otherwise it sounds a little bit incomplete. So next week again we'll be discussing this thing, and then we'll be discussing in an isotropic soil how we can draw the flow net, uh, and how we can then calculate. After that, we will be seeing how we can calculate the seepage pressure, the factor of safety for piping, and what is quicksand condition. All those things we will be looking into the next lecture. So now let us solve some very easy and simple problems from the previous week's lecture. So the first problem is that a horizontal stratified soil deposit consists of three layers. Okay, so each uniform in itself. So we have three layers of soil, each are uniform, means in each layer kx and kz are actually same. Okay, so these are three layers are there, and the permeability of each of the layers are given. So we have three, sorry, so we have three layers of soil. Okay, three layers of soil. The thickness is also given. So this is 6 meter, this is 3 meter, this is 12 meter. Okay, and the permeability of each of these layers are given. Means the K value, coefficient of permeability of each layer is given. For this one it is 80 minus 1, 80 to the power minus 4 cm per second. For this one is 50 into 10 to the power minus 4 cm per second. And for this one is 15 into 10 to the power minus 4 cm per second. Okay, so we have three layers of soil, and for each of this layer the coefficient of permeability is given. Now we need to find out the effective permeability in the horizontal and vertical directions. So please find out how we can. So directly just using formula we can find it out. So let us calculate this, how you can calculate. So first let us calculate for horizontal flow. So when the flow is like here, okay, fluid horizontal, how, what will be my effective permeability or equivalent permeability? So what was the relation, if you can remember, what was the relation for K horizontal? What was the relation? So nothing but K1 into H1 plus K2 into H2 plus K3 into H3 by H1 plus H2 plus H3, right? So we have K1, we have K2, we have K3, everything we have. H1 is 6 meter, H2 is 3 meter, H3 is 12 meter. Okay, so we have H1, H2, H3. So we can use this relation to find out our horizontal flow. What the horizontal flow will be, if we put all the values, it will be 18 into 10 to the power minus 4 cm per second. Similarly for vertical flow, so my vertical flow, what was my vertical flow? In my vertical flow, my head loss, there is the sum of head loss. The total head loss is the sum of the total head loss, and the flow in each layer is actually same. Is the velocity of flow in each layer is same. So using those two relations, we determined the equivalent hydraulic conductivity is this one. So we already determined it. So if we just put the values here, we will find the vertical equivalent vertical hydraulic conductivity as 13.04 into 10 to the power minus 4 cm per second. So one important thing if you note here is that the horizontal hydraulic conductivity by kh is always greater than the equivalent hydraulic conductivity in the vertical direction. Okay, so my equivalent hydraulic conductivity in the horizontal direction is actually always greater than the equivalent hydraulic conductivity in the vertical direction. So here we got 18, here it was vertical was equivalent vertical was 30. So let us look into the next problem. So the soil layers, so I will draw for you the diagram. The soil layers below have a cross sectional area of 100 mm into 100 mm each. The permeability of each soil layer is 10 to the power minus 2, 3 to 10 to the power minus 3, and 4.9 to 10 to the power minus 4 centimeter per second. Find the rate of water supply. So let me just draw it. So soil layer is actually like this. Okay, so this I have, see this one is known to me. So H1 is 150 mm, H2 is 150 mm, and H3 is also 150 mm. Okay, these are three soils, right? And they have same cross section. The permeability of Ka is 1 into 10 to the power minus 2 centimeter per second. P is 3 into 10 to the power minus 3 centimeter per second. C is
Sir, it's a 100 H1 H2 H3.
no 150. All are
So
150. Cross section is 100. Cross section out of plane
but
in the other direction, which we cannot see here. The other direction.
okay. No, but in problem it's a 150 centimeter. How we can know?
What? No, no, it's given in the question actually. So I did not I did not draw the figure below. So it was given in the question. So all this data, yeah, all this data is given in the question. Okay. And also one more thing, the total head loss means the head loss from here to here. It's also given. This is my 300 mm. Okay, this is also given to you. The total head loss from here to here, the total head loss that is occurring from here to here, entry to exit, it's 300 mm. This is also given. So all this data, whatever is given, written here, is given. So now can we uh, find out the first? Can we find out the equivalent hydraulic conductivity? So tell me which hydraulic conductivity should we use? Should we use this relation or should we use this relation? Please tell me, the horizontal flow relation or the vertical flow relation?
Horizontal flow,
Which, why horizontal?
because the layers are in line and the soil layers cross section permeability of is
See, no, but see, in horizontal case, what was the thing? In horizontal case, my head loss, okay, head loss along all the layers are same, right? But all head loss along all the layers are same, but the flow along each layer is different. But if you see here, it seems like it's horizontal, but it's actually vertical, right? Because the head loss from here to here will be different. The head loss from here to here will be different. My head loss from here to here will be different. My total head loss in each of these will be is given as 300. But it's not that each HA is equal to HB is equal to HC. Okay, my head loss will be different. And also one more thing, you will see the flow will be same in all, means the velocity of flow will be same from the equation of continuity, means VA is equal to VB is equal to VC. Here in this case, the velocity of flow at this cross section should be equal to the velocity of flow at this cross section, obviously, because there is, I should follow my continuity principle, right? Basic continuity principle, which the law of conservation of mass. Continuity principle is nothing but law of conservation of mass. So at each cross section, my velocity of flow should be same. It means the velocity of flow is same in each of the soil layers. So this actually looks like horizontal flow, but actually this is the case of vertical flow. So let us go back to the vertical flow once. There was the, yeah. So in vertical flow, my head there is different heads. Total head is the sum. Head loss is the sum of head losses in each of these layers, right? And in the horizontal flow is actually my head loss here and head loss here. Head loss here and head loss here is actually same. The head loss is same in all the layers in horizontal flow. And vertical flow, head loss is different in all the layers. So this condition actually corresponds to this vertical flow condition. Okay, when my flow is same in all the layers and my total head is equal to the sum of all that. Head loss is equal to sum of all that. So this problem actually looks like my horizontal flow, but is actually a vertical flow. Means corresponds to the vertical flow scenario which we studied before. Okay, so actually, so we need to use my k equivalent formula for my k equivalent relation for my vertical flow case here. So if we put all the values here, we will find we'll get the equivalent conductivity as Km. Now it has been asked to us to find the flow, total flow. So what is my total flow? Is K equivalent into I into area, right? So what is my K equivalent? K equivalent is 1.2 into the power minus 3. What is my I? Total head loss. Total head loss is 300. This 300 is occurring along a length of 450. Total head loss from here to here is given as 300 mm, and this 300 mm is occurring along this length h1 plus h2 plus h3. So 450 into area. Area is nothing but my cross sectional area, which is given as 100 mm into 100 mm. So 10 centimeter into 10 centimeter. So if I do this, I will get it as 291 cm³ per hour is the total flow. So this is actually pretty conceptual because it looks like as if the flow is horizontal, but is actually a case of vertical flow because my head will actually be changing everywhere. Means head loss here it will be different, head loss here it will be different, head loss here it will be different. Okay, that's why we are using this relation, this particular relation, because head losses will be different, and sum of HA plus HB plus HC, small HA plus small HB plus small HC is equal to 300 mm. Okay, the total head loss is 300 mm, but head loss in each of these layers are actually different. This is a very simple problem. So it is given that the following data were recorded in a constant head permeability test. So internal dia of the permeameter is 7.5 centimeter. Head loss over a length of 18 centimeter is given as 24.7 centimeter. Quantity of water collected in 60 seconds is this much. Porosity of soil sample is also given. Now we need to calculate the coefficient of permeability, discharge velocity, and seepage velocity. Okay, these three things we need to calculate. So to calculate the velocity, first we need to find out the coefficient of permeability, right? So first let us try to find out the coefficient of permeability. So this is a constant head permeability test. So if you remember this for a constant permeability test, we had already this one already found out a relation, but let us keep that aside. We will be solving it one by one using a basic like common sense. So first let us find out the area of the soil sample. So what is the area of the soil sample? So the internal dia of the permeameter means uh, the device inside which the soil sample is kept. Okay, so area of soil sample I can get it from here, pi by 4 into d square 7.5 square, which is nothing but 44.18 centimeter square. So we got the area of the permeameter from here. That is area of the soil sample. Now total head lost is my 24.7 centimeter. Okay, length over which the head loss is occurring is my 18 centimeter, right? And the time t is given as 60 seconds. Now hydraulic gradient I can find out from h by l. If I write, I can find out the hydraulic gradient, right? So 24.7 by 18. Okay, hydraulic gradient is nothing but 1.372. Hydraulic gradient I got. Now discharge. How to determine the discharge? Okay, discharge is nothing but volume by time. So what is my volume? My volume is 626 milliliters. Okay, so 626 by 60 seconds, but time is 60 seconds. In 60 seconds I am collecting 626 milliliters, right? So it will be 10.433 centimeter cube per second. Okay, so I found out my q, that is the this one discharge that is happening. Now I know that q is equal to kia. So this q I found out as 10.433. Ki need to determine. What is my I already found out as 1.372, 1.372. And what is my area also I found out 4.18. So from here I can find out my coefficient of permeability of hydraulic conductivity is 0.172 centimeter per second. Okay, so this coefficient of permeability I have determined. Now the next task is to determine the discharge velocity and the seepage velocity. Okay, so can you what was the relation between the discharge velocity and seepage velocity? Can you remember? What was the relation between seepage velocity, or what you can see it as superficial velocity? This one is not discharge velocity. You can call it a superficial velocity. What was the relation between the superficial velocity and seepage velocity? If you can recall, what was the relation? So, what was the relation between Vs and V? Obviously, those two are not were not equal, right? Those two were not equal. My seepage velocity was always greater than the discharge velocity, right? And so by seepage velocity was given by discharge velocity by n, where n is the porosity, right? So let us first find out my discharge velocity. Discharge velocity is nothing but k into I, nothing but 0.172 into 1.372 will come out as 0.236 cm per second. Okay, just calculate. Yeah, 0.236 cm per second. Now the porosity is given to you as 44%. It's already given to you in the question. So we can calculate the seepage velocity as 0.236 divided by 0.44. 0.236 divided by 0.44, nothing but 0.536 per second. So we can see again that my seepage velocity is always greater than the discharge velocity. Okay, I hope this was clear. So what we did was constant head permeability, so the head remains constant always. So this head always remains constant throughout the test. So we had the Q value, discharge value. The water collected was 626 ml in 60 seconds. So we found out the discharge value. We also had enough data to calculate a hydraulic gradient. So we had all the data. So we know my discharge total discharge is equal to Q is equal to KIA. So using that relation, we could find out the quotient of permeability or hydraulic conductivity. Then using the hydraulic conductivity, found out the velocity of flow, velocity of discharge, and then using this relation we found out our seepage velocity. So now let us go to the next problem. So the next problem is that in a falling head permeability test, the head causing flow was initially 90 centimeter and it dropped 6 centimeter in 15 minutes. Okay, so my initial head H1 was 90 centimeter and H2 was how much? So in H2 means when it drops 6 centimeter in 15 minutes, right? 6 centimeter in 15 minutes. So what will be my final this one final head? If my initial head was 90 centimeter, what will be my H2? It's dropping 6 centimeter in 15 minutes. So what will be my H2? 90 minus 6, 84 centimeter. So this much is happening in T is equal to 15 minutes, right? So this data is available to us. Okay, and nothing is actually, if we look into the question, nothing is actually mentioned about the area of the soil sample, the length of flow, then my area of the tube. Nothing is mentioned about all those things. Okay, so in the question it's finally asked that how much time is required for the head to fall to 45 centimeter. Means when my H2 is 45 centimeter, that time how much time will be required? So from 90 to 84 centimeter it's happening in 15 minutes. So how much time will be required from 90 to 45 centimeter? That you have to find out, right? So How can we find out? So first what we need to do is that this is my available data, right? So using this available data, we need to represent the unknown terms. The unknown quantities, if we remember the equation of the falling head test, the quantities were my area of the tube, my length of flow, my area of the soil sample, those things are unknown. So what we will do is that we will find out the those things in terms of this, the known terms, right? So let us do this. So you know that K is equal to A L A T log H1 by H2. We if we want to write this in terms of base with log E, we can write 2.303 A L A T log H1 by H2, right? So H1 you know, H2 you know, T you know, correct? So now let us write 2.303 AL by AT, okay, is nothing but T by log H1 by H2, right? So this we are representing in terms of the known quantities. So T you know, 15 divided by log 90 by 84. So if we do this, 500.61 minutes. So we determined the unknown quantities. These are the unknown. This A, L, H, sorry, not L, should not be here. So these are my unknown quantities. So A is unknown, L is unknown, K is unknown, capital A is unknown. So these unknown quantities we represented in terms of the known quantities, and we found out the value, right? Now we want to find out when my H1 is 90 and my H2 is 45, what is the time, right? So let us again write the relation. So my K is 2.303 AL by AT H1 by H2. If we rearrange, it will be 2.303 AL by KA log H1 by H2, right? This one we all this we already determined here, 500.61. So we can directly write is it 500.61 into log 90 by 45 is log 2. So my final answer will be 150.70 minutes. Okay, so in 15 minutes my head is dropping from 90 centimeter to 84 centimeter, but for the head to drop from 90 centimeter to 45 centimeter, it's taking 150.70 minutes. So first we represented the unknowns in terms of the known, and then we used that relation to find out the final answer, right? So this was the case of falling head test. So before we, the first problem, this previous problem was for the case of constant head test. Now it is the case of the falling head test. So very simple. These are very simple direct formula based questions. So now let us go to the next question. Okay, so the next question is that a well penetrates the unconfined aquifer having a saturated depth of 100 meter. Okay, a discharge is 250 liters per minute at 12 meter drawdown. Assume equilibrium flow conditions and homogeneous aquifer. Estimate the discharge at 18 meter drawdown. Okay, okay. So it is the case of that pumping out test, right? So in pumping out test, it's given that well, actually this is the well actually penetrates. So water, this is the water table, right? So the having a saturated depth of 100 meters. So this is 100 meters. This is the saturated depth. This is the 100 meters, and the discharge is 250 liter per minute at 12 meter drawdown. Means that when the drawdown means the height from the top, okay, height from the top is 12 meter. 12 meter when the water is here, from here to here, so we are pumping out, so water level will reduce here. So when this is 12 meter, my discharge is actually 250 liters per minute. So we need to calculate the discharge when in this well my drawdown is 18 meters. From here to here it's 18 meters. When it is 18 meters, we need to find out the uh, discharge. Okay, so actually we already saw there is a relation. Okay, so k is given by 2.303 q log, see this is base 10, that's why 2.303 is coming, r by r naught by pi h square minus h naught square. Okay, so this is the, so previously, see, previously actually what we studied was that where there was two test wells, that condition, right? So now this is a different case. Okay, here we are just drilling one well. Okay, this is that case. Okay, in that case actually this relation defines the flow. This relation actually defines the flow. Now, or if we rearrange the terms, we can get pi into k by, this is actually similar to the previous problem. So here also we will be representing the unknowns in terms of the knowns, and then we'll be using that to find out the final answer. Same, exactly same, similar to that previous question. Just we here the case that was a this one falling head test, and this one is one of the in situ test, the pumping out test. The tests are different, but the concept is same. That's great. So what is my q? Q is given as 250 liters per minute. Okay, and what is my h square and h square? See, h square is the total height, this total saturated depth, that is given by h square, capital H. This is 100 square. And what is the h naught? H naught, h naught is the after we are after we are pumping out, the height will reduce. Here the height is reducing, from here fast it's coming here, it is reducing. So what will be that height? 100 minus 12. Okay, drawdowns means the height from the top. Okay, so if this is 12, so what will be this? This is nothing but 100 minus 12. 100 minus 12 is what? 88. So 88 square. So if we do this, we will get test 250 by 2256. So we represented the unknowns in terms of the knowns, right? Now it is given when my drawdown is 18 meter. So initially it was 12 meter. Okay, so then it has come down to 18 meter. So when it has come down to 18 meters, what will be h naught now? H naught will be 100 minus 18, right? So in that case, 800 minus 18 is 82. Now my h naught will be 100 minus 18 equal to 82 meter. So now in this case, we need to calculate the discharge. So let us write the formula again. Okay, and this part we already calculated, which is nothing but 250 by 2256, right? So just calculate, comes out to test. So problem is actually pretty similar. Problem number 4 and problem 5 are actually exactly same, but the formulas that we are using is different because the situation is different. One, it was the case of falling head test, another is the case of pumping out test, but the concept is same. Okay, So here also the unknowns we represented in terms of the knowns, and then we used it to find out the final answer. Yeah, now let us see the next problem. The next problem here we have that a 30 centimeter dia well penetrates to a depth of 25 meter below the static water table. So this is the well, this is my water table. So this is 25 meters. After 24 hours of pumping at 5,400 liters per minute, the water level in the test well at 90 meter is lowered by 0.53, and in a well 30 meter away is lowered by 1.11. So here are two test wells. Okay, one is 30 meter away and the other is 90 meter away. Okay, so the water here is 1.11 and the water here is 0.53 meter. Okay, these things are given. These things are given. Also, this is dia is given as 30 centimeter. Okay, the flow is also given to you. Then after in time t is equal 24 hours, this is my flow that is obtained. Okay, so now let us first write all the values, right? So my total depth is 25 meter. Okay, it is my r1. R1 is 30 meter. R2 is 90 meter, which is my h1. H1 is 25 minus 1.1. It is nothing but 25 minus 1.1. 23.89 meter, and h2 is 25 minus 0.53. 25 minus 0.53 is 24.47 meter. So h1 h2 I got. H1 is nothing but this, h2 is nothing but this. So h1 h2 I got. Right, now also my flow is given. Flow is nothing but 5,000. Flow discharge is nothing but this is the discharge. Okay, so this is this, if I represent in terms of meter cube per second, this will be 0.09 meter cube per second. Okay, now we have all the data that is required to us. So now if we remember the expression that we got for permeability, it is nothing but 2.303 q log 10 r2 minus r1 by pi h2 square minus h1 square. Now you have q value, it's given to you. The steady state discharge, it's given to you. R2 you have, R1 you have, h2 also is known to you, h1 is also known to you. So if you just put all the values, we can get the value of our coefficient of permeability. So let us do 24.47 3.89 and if we do, we'll get the flow as 1.1218%. So this is my coefficient of permeability, right? So now let us so in the question C, it is not, so finally what is asked to us? It is asked to us what is the transmissibility of the aquifer. Now what is aquifer? Aquifer means a soil mass which can hold large amount of water. So this soil mass here, the soil mass which is there, this soil mass is actually holding uh, a large amount of water, right? So this is called a aquifer, right? Unconfined aquifer means from all sides my water can enter, that's why it's unconfined. Okay, so if confined aquifer means up it's impervious, ground is impervious and center it's water is there. Water can be stored. This is known as confined aquifer. Now our case is unconfined aquifer. Okay. So we need to find the transmissibility of the transmissibility of this one. Transmissibility of aquifer means transmissibility is a property which actually shows us how much water aquifer can actually hold, or how much water a aquifer can actually allowed to flow through it. So that is the property called transmissibility. So there's actually relation for transmissibility. The transmissibility T is actually nothing but my coefficient of permeability into the height, saturated height, or the height of my aquifer. Aquifer here is given to me. The aquifer is 25 meter. Okay, the total height is 25 meter. So we know this 25 meter. We also know our k value. So k, if we just multiply it by 25, we will get 1 point, sorry, 0.028 meter square per second. That's the transmissibility of the aquifer. Okay, transmissibility, it's asked. Remember, transmissibility is nothing but k into h. H is this height, which is 25 meter, into k. K is nothing but the coefficient of permeability of the soil, which you just determined. Okay. The next question: the coefficient of permeability of fine sand is this much. As a void rate ratio of this much, it's given. Estimate permeability of soil if sand is compacted to a void ratio of this much. Use. So what is a Kozeny carbon formula? So in here it is given that at one void ratio we have a coefficient of permeability. Now if the sand is compacted, see, it's granular soil. Okay, granular soil, coarse soil. So in course of coarse soil, if the soil is compacted, means tightly packed, if the soil particles get tightly packed, then obviously the permeability is going to change. Right, obviously the permeability going to change. So at one word ratio, we have the coefficient of permeability. Now it's been asked to us that other word ratio, means at lower word ratio, what will be the coefficient of permeability? Okay, and we are being asked to calculate this using the Kozeny-Karman formula. So what is the Kozeny-Karman formula? If you remember, K is nothing but C into E cube plus 1 plus C. So C is a constant, right? So you can write K1 is equal to C E1 cube by 1 plus E1 cube. Then K2 you can write it as C E2 cube by 1 plus E2 cube. C is a constant, right? For a particular soil, C is always fixed. So here the soil is same, thus the void ratio is changing, right? So for a particular soil, my C is going to be the same. So now if you want to write K1 by K2, C will get cancelled out, right? So we will get E1 cube by 1 plus E1 cube by E2 cube by 1 plus E2 cube, correct? Now if you just put all the values, say K1 you are taking as 0.022 and K2 you need to find out, and E1 you know 0.72 cube by 1 plus 0.72 cube, and E2 you need E2 also you know 0.57 cube by 1 plus 0.57, sorry, there is no cube below, right? There is no cube here. 0.57 cube by 1 plus 0.57. So you know all these values. So if you just calculate it, you will get your K2 as 0.012 centimeter per second. Okay, so at one word ratio, I know my hydraulic conductivity. I need to find out my hydraulic conductivity at other word ratio. So I use the Kozeny-Karman formula. Easily I could find out the hydraulic conductivity. Okay, two word ratios were known and one coefficient of permeability is known. So other coefficient of permeability is the second word ratio. I could easily calculate it. Yeah, so now let us come to this problem. So this problem, so the first this case was actually discussed already in the previous class. So this was the second case was actually I told to actually solve by yourselves in the previous discussion. So nevertheless we will be solving the second problem so that we get some clarity. Okay, let us solve. So what, so this case what is given is that we need to find out the pressure head, elevation head and total head at entry and exit points, and also at this A point, right? We need to find all these things. So now let us first make the table. Okay, so first we will write the elevation here. Elevation is the point, elevation of the point is the point, just we will name the point using the elevation. Okay, elevation of the point. Then we will be writing the elevation head, then the pressure head, the total head and the head loss. Okay, let us, so first let us see, at see. Now if you look into this, the head at this point is high, see, very high, right? So the flow is actually occurring in this direction. Okay, the first point is my 0 point. At my 0 point, the 0 point, what is my elevation head? Elevation head, if I consider this as the only this as my data, what is my elevation? Elevation head is 0. What is my pressure head? Pressure head means the head to the water pressure. What is my pressure head? It is 9. You can see here, from here to here, water is up to here, it's rising up to there, so it's 9. So it's 9 meters. So what is my total head? 0 plus 9 is equal to 9. Head loss is obviously 0 here. So now let us come to 1. Elevation 1. So 1, so at elevation 1 it's my A point, so we will look into it later. Now let us come to the fourth point, exit end. This is the entry end, this is the exit end. Now exit end, what is my elevation head? Here what is my elevation head? If you can tell what is my elevation head, you can look and tell. What is the elevation head at this point? From here to get nothing but 4. Elevation head is 4. What is the pressure head? 5 in 5 1 meter. See, only this much height. Okay, so 1 meter. So what is the total head? 9. So what was my head loss here? Head loss here, 9 minus 5 is equal to 4 is my head loss. Now let us come to the fifth point, means this point. What is my elevation head here? 5. What is my pressure head here? 0. What is my total head here? Head is 5 plus 0 is 4. 4. Head loss was 4. Now how to determine my elevation head? I know, see, at this point, A point or 1 point, what is my elevation head? I know it's 1. But do I know my pressure head? No, right? How can I calculate the pressure head? So what we need to do is you need to actually back calculate it. So from entry to exit, how much head loss is occurring? 4. How much head loss is occurring? 4. And about along what length is the head loss occurring? This head loss is occurring along 4-meter length. See, this is the entry, this is the exit, right? So along from entry to exit, see, from entry to exit head loss is 4 meters, right? So, and this head loss of 4 meter is occurring along the length of 4 meters. This is also 4-meter length height. So the hydraulic gradient is 4 by 4 is nothing but 1. Okay, now hydraulic gradient I got as 1. Now tell me, if my hydraulic gradient is 1, so along 1 meter distance, say from here to here, from 0 to 1, along 1 meter length, what will be my what will be my head loss? See, my I is nothing but head loss by length, right? So now I know my length. So along from here to here, what will be my head loss? Nothing but I into 1. I into this distance will give me the head loss in that part. Hydraulic gradient into that height will give me the head loss at that point. So head loss is nothing but 1, right? Head loss is nothing but 1. Now see, If head loss is 1, what should be my total head? My total head should be what? My total head at entry it was 9, right? From 9 you are losing 1. So now here my total head of which should be 8. That's why there is head loss 1, right? At entry it was 9, and I know from entry to A there was a head loss of 1. That means what? My total head at A was 8. That's why I am saying my head loss is 1. So if my head loss is 1 here, so obviously my pressure head should be 7 here, right? Obviously my pressure head should be 7. Then only I will get total head is 8. So that's how we back calculate the pressure head here at a point. Okay. From the hydraulic gradient, we get the head loss. From the head loss, we get the total head. From the total head, we get the pressure head. So we are back calculating. Okay. This way we can get. So similarly, for this case also I had shown in the last class, and this one I showed. Now it is being asked to you, what are the superficial and seepage velocities, right? So superficial and seepage. So it is very simple. So K is given, everything is given. K is given to what is the superficial velocity? K into I. Okay. So K is 0.1. What is my I? What is my I? My I is 1. So K into 1 is 0.1 cm per second. Right? So what will be my superficial velocity? Vs, V by N, 0.1 by how much? It's given na 33%, 0.33. So 0.1 by 0.33 is equal to 0.3 cm per second. Done. Very easy. Now let us go to this problem. This is the last one. Yeah, two problems were there. Huh? Yeah. So in this problem, two soils are arranged like this. Okay, A and B are arranged that to determine the quantity of flow in this case. So here obviously flow is occurring this way. We need to determine the quantity of flow. This is very simple, very simple. This is just the case of our this flow, the horizontal and the vertical flows that we solved before, same to that. So please tell me, how can we solve this one?
Vertical flow.
This one will be vertical flow because my head loss in these two soils will be different, right? Now it is asked to us determine the quantity of flow. Now the quantity of flow will be same, means the qa is equal to qb, right? So what is my qa is nothing but ka into ia into q is equal to aa. Okay, and qb is nothing but kb into ip into ab, right? So my both these flows in both the soils are going to be same. Okay, so if I just determine one, I can, it will be obviously equal to the another. So now let us solve this one by one. So let us see at what is the total head at this point. Please tell me the total head at this point. At elevation 3 meter, what is the total head? The elevation head is 3. Okay, and what is my pressure at 1.5? So my total head is 4.5 meter, right? Now what is my total head here at elevation 0 meter? What is my total head? Elevation head is 4.5, pressure head is 0. So my sorry, elevation head is 0, not 4.5. Elevation head is 0, total pressure head is 0, total head is 0. Yeah, isn't it? So total head loss of 4.5 meter is occurring when my from here to here. A head loss of total 4.5 meter is occurring from here to here. Now this total head loss is equal to head loss in A plus head loss in B, right? So here there will be some head loss, here there will be some head loss. So head loss in A is plus head loss in B is going to give me my total head loss. So let us mark it as one equation. Now the second thing that we know is that the velocity of flow in both these soils will be equal from the equation of continuity. My velocity of flow will be this, VA is equal to going to be equal to VB, right? My VA is going to be equal to VB. So VA is, I can write Q into IA, KB into IB. I can write this. Now K is K, I know this, right? I can write it as head loss in A divided by the length of flow. Length of flow is how much? How much? C to 1.5 meter, right? Equal to KB into HB by 1.5 meter here, 1.5 meter. So here I get another relation between HA and HB. So HA by HB I have equal to KB by KA. So KB and K is known to me. KB is 0.01, K is 0.1, right? So HA by HB is equal to 0.1. So these two equations I have. HA by HB is equal to 0.1 and HA plus HB is equal to 4.5. These two relations I have. Now if I solve these two relations, these two, I can get the this one HA and HB. I can get HA and HB. Now if I solve these two, I will get HA as 0.41 meter and HB as 4.09 meter. So if I solve these two equations, I will get HA and HB, right? So if you see this, my total head loss is 4.5 meter. From here entry to exit, my total head loss is 4.5 meter. Out of that 4.5 meter, 0.41 meter of head loss is occurring in this soil and 4.09 meter of head loss is occurring in this soil, right? Now ultimately what are we asked? We are asked to find out the flow. Okay, yeah, flow. So the flow is nothing but Q is equal to KA. See, these are going to be equal. These both are equal, na? So AA. So what is my K? 0.1 into 10 to the power minus 2 into IA. IA is nothing but 0.41 meter by 1.5, because I know now my head loss of 0.41 meter is occurring along a length of 1.5 meter. Okay, this I know, into the area. So area is 1.5 I am considering, this is 1.5, then other direction is actually 1 I am considering. So into 1. So if I solve this, I will get this as 4.1 into 10 to the power minus 4 meter cube per second. So this is going to my flow. Okay. Just a second, I will just check. I think this is vertical row, right? So 3 divided 0.01 K I is point 4 I. Yeah. So one more thing. So we solved it like this. Okay. Now another alternatively also we can solve this. How can we solve this? Please tell me. So let us go to the direct. This one we solved it more conceptually, right? Step by step we solved it. Conceptually we solved it. Okay. How are actually things happening inside? We solve this. Actually how things are happening. But this can also be solved in a very easy way, right? How can we solve it? Please find out K equivalent. In this case, this is the case of vertical flow, right? So please find out K equivalent. What is the formula? H by H1 by K plus H2 by KB. You use this formula. Please find out. What is my height? Total height from here to here is 3 meters. H1 is 1.5, K is 0.1 plus H2 is 1.5, 0.01. You calculate this. Please find it out. It will be 0.0181 centimeter per second. You know Q, know K equivalent now. Okay. You know K equivalent. K equivalent you know. So how can you find out Q? Q equivalent will be K equivalent into I into area. Okay. So what is my K equivalent? I found out my K equivalent is 0.0181. 0.0181 into what is my I? I is nothing but I, you already told that my total head loss of 4.5 meter is occurring from here to here. So so I will be equal to 4.5, and what is the what is the length of flow? It is 3 meter, because from here to here is 3 meter. So 3 meter into what is the area? Area is 1.5. Okay. If you do this, you will get the same answer. Answer will be same. 4.1 into 10 to the power minus 4 meter sorry, meter cube per second. Meter cube per second. Okay. Answer will be same. So this one directly we can calculate easily, very easily. But this problem is actually how the way you solved it is, it's very conceptual. Okay, step by step we solved. We saw how much head loss is occurring in one soil, how much head loss is occurring in other soil. Like that we solved it. Okay, in question exam it can come that please draw the pressure head, elevation head, total head diagrams. Okay, at that time we need to solve it like this. But if it's asked you to only determine the flow, then we can directly determine my K equivalent using this formula. The first you have to see if it's horizontal or vertical flow, then you can use the K equivalent formula, and then directly you can find out the Q's like this. But if it's asked to you how find the find at all points, please find out the pressure head, the data head, the total head, then we need to solve it like this. Okay. Okay, similar to this, one more problem is there. One more problem. This is the problem. So this one, let us solve. Normally see, this one is a case of horizontal or vertical flow. This is the case of horizontal or vertical flow. It's a case of horizontal flow, right? Because see, flow is equal to total flow will be equal to the flow from here to here. Sum of the total flows, that is the velocity in this and this will be different. The flow of QA, flow of soil B will be summed together to get the total flow, right? But the head loss in two of the soils are same. So this is the case of horizontal flow. So what is my K equivalent? K1 H1 plus K2 H2 by H. So 0.1 into 3 plus 0.01 into 3. One second. Just a minute. Not 3. It'll be 3. No, right? It will be 0.75. 0.75 into 0.75 by 0.75 plus 0.75. So let us calculate this. 0.1 into 0.75 plus 0.01 into 0.75 by 0.055 centimeter per second, right? K equivalent you know. Now you can find out the total flow is K equivalent to I into A. So what is the total head loss? Here it was, here the head was how much? Here what is the total head at this point? What is the elevation head? Is 3, 4.5, and here the head loss, total head loss is 4.5. The K equivalent is 0.055, 0.055 into 4.5, occurring along the length of 3 meter into the area of cross section is nothing but 1.5. If we do 0.55 into 4.5 by 3, 1.2375 into 10 to the power minus 3 meter cube per second. Okay, so this will be total flow. The same problem you can actually solve in this manner also. Okay, in this manner also how we solve, like in the conceptually how we solve step by step, this way also you can solve to find the, so you have to solve it this way if it's asked to you to find out the pressure rate, determine everything. Okay, but say it's asked us to determine the quantity of flow, then we can directly determine the K equivalent from a known formula. First you have to identify it, whether it is a horizontal flow problem or a vertical flow problem. Then you use the correct K equivalent formula to find out the K equivalent. Then from K equivalent you find out the total flow, nothing but KIA, you know the formula. I, you know the head law, this one hydraulic gradient, that one is also will be given to you. Area will also be given to you, so using that you can find the total flow. Okay, so I suggest you please try to solve this problem. Try to what I suggest is, see here, you find out the total flow, right? So your homework will be to find out QA and QB separately. Okay, so this will be your homework. So what is the, so out of this 1.23 2375 10 to the power minus 3, how much is coming from A soil and how much is coming from B soil? So that will be the homework. So we can find that out easily. So that will be the homework. How much, what is the distribution in the two? Okay, how much is coming from this soil, how much is coming from the this soil? Okay, so with this we will end today's discussion, and in the next week we will be again looking into that anisotropic soil. For anisotropic soil, how is the seepage, how we draw the flow net. Then we will be looking into the flow nets for art dams, and then we will be going, and after that we will be entering into the where how you can calculate the seepage pressure below any hydraulic structure. That things we will see how you can calculate the factor of safety at the exit gradient, all those things. Then we will go into the in situ stresses. In the in situ stresses are also very important, it's very important chapter. So we will see learn the concept of effective stress, what is effective stress, what is total stress, what is pore water pressure, all those things we will learn. And why is effective stress so important to us, and how all the soil, actually all the soil theories are actually strength theories are actually based upon the effective stress principle. So how and why it is important, effective stress is actually important to us, all these things we will be actually looking into in the next week. Okay, I hope all these problems are clear, and I really suggest that you find this out, Q and QB separately, so this will actually help you in clearing up your concepts. Okay, so the solving procedure will be, solution procedure will be quite same to this what we solved here, so it will actually clear up the concepts, right? So I hope everything was clear. So if there is any doubt, you can contact me anytime, and I will also upload all these things in the Google Drive and YouTube, so you can refer to them at any time. Okay. Okay, so thank you.